You ever look up at the stars and just wonder, how big can things really get out there? Well, today we're going to find out. We're going on a hunt for the undisputed heavyweight champion of the entire universe. Let's get into it. So, the big question, what is the largest star out there? Sounds simple enough, right? But the answer, well, it's pretty mind-bending. To really wrap our heads around it, we can't just jump to the end. We've got to start small, with things we kind of know, and then scale our way up, all the way to the unimaginable.
Okay, so before we can even talk about the biggest star, we have to know what a star is. And just as important, what it isn't. Turns out there's this really fascinating gray area out there, a whole category of things that are almost stars, but not quite.
Let's take Jupiter, for example. Huge gas giant, right? It's even made of the same stuff as the sun, hydrogen and helium. But it just doesn't have the oomph, the sheer mass, to light up. Then you've got the next step up, a brown dwarf. You'll often hear these guys called failed stars, and that's a pretty good description. So a brown dwarf is the universe's ultimate almost there. I mean, it's way more massive than a gas giant. We're talking anywhere from 13 to 90 times the mass of Jupiter, but it still isn't heavy enough to kickstart that full-blown hydrogen fusion that makes a star a star. Think about that for a second. You could slam 90 Jupiters together and you still wouldn't have a star. They do give off a little glow, but it's faint just from some small-time fusion reactions. All right, enough with the wannabes. Let's get to the main event, main sequence stars. This is the real deal. It's that long, stable, adult part of a star's life. Our sun is in this phase right now. It's when they're just steadily fusing hydrogen into helium in their cores and pumping out incredible amounts of energy. Now here's the key thing you gotta remember for these main sequence stars. There's a really simple rule. The more mass you have, the hotter you get, the brighter you shine. But, and this is a big but, there's a huge price to pay. The bigger they are, the harder they fall. They live fast and die young. And this table just lays it all out perfectly. Check out the red dwarf on one end. Tiny bit of mass, super dim, but it'll keep chugging along for trillions of years. Now look at the other side, the blue star. It's maybe 10 times the sun's mass, but get this, it's a whopping 20,000 times brighter. But what's the catch? It completely burns itself out in about 20 million years. That's nothing. It's just a blink of an eye in cosmic terms. So you'd think, logically, that this pattern holds, right? More mass equals bigger, hotter, brighter. So the most massive star we've ever found must also be the largest star by size. Makes sense. Well, let's just say the universe has a little plot twist for us. Okay, say hello to R13A1. This thing is the heavyweight champion of mass. We're talking 315 times the mass of our sun, all packed into one star. It is an absolute beast, shining almost 9 million times brighter than the sun. Just insane. But wait, take a look at its size. Even with all that mass, 315 suns worth, it's only about 30 times wider than our sun. That means it's unbelievably dense, super compact. So there's our answer. The most massive star is definitely not the largest star. Huh. That means the real secret to getting ridiculously, mind-blowingly big has to be something else. So if just packing on more and more mass doesn't make you the biggest, what does? How does the star become a true cosmic giant? Well, here's the paradox. The secret is, it has to start dying. It works like this. See, when a star starts to run out of hydrogen fuel in its core, gravity takes over. The core crushes in on itself, and that makes it get even hotter. This heat is so intense, it ignites a new shell of fusion around the core, and this new energy pushes the star's outer layers out. And I don't mean they just expand a little bit. They swell up to absolutely enormous sizes. And hey, if you want a sense of what this looks like, just look at our own sun's future. Yep, it's going to happen to us. In about 5 billion years, it's going to puff up into a red giant, swelling to maybe 200 times the size it is now. It'll completely swallow Mercury, Venus, and, yeah, probably Earth too. So if a regular old star like our sun can get that big at the end of its life, what do you think happens when the most massive stars start to die? Well, they don't just become giants, they become hypergiants. And these are the real heavy hitters, the true contenders for the biggest star in the universe. Okay, let's meet the finalists.
First up, we've got the Pistol Star. This is a blue hypergiant, super hot, crazy bright. It's already 300 times the radius of our sun. That's immense. But believe it or not, this is just the warm-up act.
Next on the list, Rho Cassiopeiae, a yellow hypergiant. This one comes in at around 500 times the sun's radius. As it got older and puffed out even more, it cooled down a bit, going from blue to yellow. At this point, we're talking so big that if this was our sun, Earth would be deep inside of it. But we're not done yet. We can go bigger.
Okay, the biggest of the big, the absolute titans of the cosmos, are the red hypergiants. These things are so bloated, so enormous and spread out, they're probably pushing the absolute physical limit for how big a star can even get. So who's the champ?
Everybody, meet Stephenson 2118. Its radius, you ready for this, is estimated to be 2,150 times the radius of our sun. Let that sink in. This isn't just a star anymore. It's basically a solar system-sized object. Look, it's almost impossible to wrap your head around that scale, but let's try. If you could fly a spaceship at the speed of light, the fastest anything can go, it would still take you almost 9 hours just to go around it once. If we dropped it into the middle of our solar system, its surface wouldn't just swallow Earth or Jupiter, it would reach all the way out past the orbit of Saturn. It's a size that it breaks your brain. So, what happens next? What's the fate of a star that gets this impossibly huge? Well, it can't last. Not like this. Being this big makes it incredibly unstable. It's really living on borrowed time. Stephenson 218 is so ridiculously large that its own gravity can barely hang on to its outer layers. It's literally blowing itself apart, constantly shedding huge amounts of its own mass out into space. And its spectacular but very short reign as the biggest star is going to end in one of the most violent ways possible, a massive supernova. But that brings us to this really beautiful final thought. The death of this giant, it isn't just an ending, it's a new beginning. All that material it's throwing out and all the stuff that will be blasted out in the supernova, that enriches the entire galaxy. It becomes the raw ingredients for the next generation of stars and new planets, starting that grand cosmic cycle of birth and death all over again. So the largest star isn't just some record holder. It's an absolutely essential part of the universe's ongoing story of creation.